Good morning. Good morning, everyone. Good to see you back. So, I'm going to give people a few minutes to trickle in, but in the meantime, I'll give you a bit of an introduction about what we're going to cover today. So, yesterday we did data and statistics and regression, which was a little bit boring, but that was everything to do with populations and samples, and then linear regression, etc. And also cumulative frequency diagrams, histograms. And I'll have that recording posted today if you're not super comfortable with that. And then today we're going to be talking about probability. So we're going to talk about theoretical probability versus experimental probability. We're going to talk about how you combine probabilities, look briefly at sort of Venn diagrams very quickly, independent events, mutually exclusive events. Then we're going to talk about dependent events and tree diagrams, which are a little bit tricky to work with. And finally, we're going to talk about Bayes' theorem, which is on the syllabus, even though it has never showed up on the exams. It is officially on the syllabus. They have a course code just for that. So we do have to cover it just in case they decide to put it on this year. Um, and especially since I imagine none of you have really practiced it before because it's not on the past papers. So with that said, I'm going to share my screen and we're going to get started. So the most basic terms you need to be familiar with are this idea of trial, outcome, and event. And in probability, a trial is just a procedure that I do that has a certain result. So it could be flipping a coin, rolling a dice, drawing a card, and each possible result of a trial is called an outcome. So every branch that the trial could go in is leads to one of the outcomes. And then an event is a collection of one or more outcomes representing certain scenarios that we're interested. So we can define um, the certain outcomes to have names like A and B. It's going to make it easier to describe them when we're doing probability. So, for example, I could say that rolling an even number is A and drawing a red card is B. You also need to be familiar with this word for sample space, which is the universe of all possible outcomes. Okay, so that's why there's the U, the set U there. So if I'm rolling a six-sided die, the sample space is the integers 1 through 6 because I can roll any possible integer between 1 and 6. And it's really important to clearly define your sample space because it's gonna be necessary sometimes for accurately calculating your probabilities. So theoretical probability is calculated based on reasoning or mathematical principles. It's about what you expect to happen, given what you know about what could happen and the likelihood of those things happening. So, if you have outcomes that are equally likely, then the probability an event is given by, let's say, P of A is equal to the number of ways that A can happen divided by the number of things that there outcomes that there are total. So, let's take the example of rolling a dice. I have six possible dice rolls, so the size of the universe, n of u is 6. And if I define a to be the event, an even number is rolled. Well, there are three possible even numbers, so n of a is 3. And thus, the probability of rolling an even number is 3 out of 6, or 1 out of 2. Now, the theoretical probability differs from the experimental probability, which is a sort of estimate based on what we've measured. And it's more to do with relative frequency than it actually does to do with probability. So if I actually conduct trials, physically in the real world, I could roll a six 3 times in a row. That's possible, even though it's theoretically quite unlikely. And the universe doesn't have to follow, strictly speaking, probability in any given moment. You can have a bit of randomness that goes in one way or another. What you do end up seeing over time is as you increase the number of trials that you perform, your experimental probability will converge towards your theoretical probability. And what that means is if I take a coin and I start flipping it, I might get heads and then heads and then heads again. That's possible. But if I flip the coin 1,000 times, the number of heads that I'm going to get is going to be very, very close to 500. Because the more total trials I do, the more probability has a chance to, exert its influence, and the more random chance should just fade into the mix. Okay? So theoretical probability tells us what's expected, and experimental probability tells us what is observed. Now, complementary events, okay? So if I have an event A, then the complement of event A is denoted A prime, and that is the event where A does not happen, okay? And since A either happens or it doesn't, then exactly one of A or A prime must happen, which means that the probability of A plus the probability of not A add up to 1. And this seems like a very basic fact. It's important that you not just kind of know it as a rule, but be so sort of uh, deeply in tune with this idea that when you need to use it in a problem, it's going to come to you naturally, and you're not going to be racking your brain for what the next step is. Okay, so we're going to talk now about the intersection of probabilities and then the union of probabilities and all of that. So if I have an event, if I have two events, A and B, then I can say that the event where both A and B occur is denoted by A, and then this little symbol means intersection, A intersection B, okay? And we're going to talk more about Venn diagrams in a second, but I do want to start drawing it because I think it's going to be helpful. If I have this is event A and this is event B, then the event A intersection B is this area in here, okay? Next. Now, the union of probabilities. This one is going to be good for a Venn diagram as well. If I have two events A and B and I'm interested in the probability that either of them occur, what I'm interested in is this total area, everything in my little Venn diagram. Now, what I can do is I can say that that is going to be the sum of two areas. I can add up this area, and then I can add in this area. But there's an issue, right? Now you see that this portion in the middle has been counted both as purple, pink, and yellow in my little diagram. So I've counted this region twice. So what I have to do is I have to subtract out the area that is in both of them. And what is that area? Well, that's the intersection. So that leads me to the formula, which is in your booklet, that the probability of A or B is equal to the probability of A plus the probability of B minus the probability of the intersection of both happening. Okay? Next slide. Okay, now mutually exclusive events. Events are mutually exclusive if they cannot both occur at once. Okay? In this case, the intersection probability is 0. So I would have P intersection B is equal to 0, and therefore P of the union would be P and B. P or B equals to PA plus PB. All right, as promised, a bit of Venn diagrams. These could show up on exams, and they're also a good tool sometimes for solving these problems yourself. You can always make a sketch. But basically, it's a visual tool for representing the relationships between sets or events. And each event is represented by a circle, and we draw a big box around all of the circles that represents the universe, the set of all possible outcomes. Okay? And this is going to help you see the intersections and the common events and unions, etc. So, for example, in this Venn diagram, we're going to try and find the size of the universe, um, the intersection of A and B, the intersection of A and C, and then the union of not A and C. Okay, that's going to be tricky. So in this universe, I have 5 things in just A, 5 things in A and C, so that's 7 so far. Then 11 things in just C. That brings me to 18, and then 21, and then 29. So I have 29 things in the universe just by adding up everything that I have in the sets that is labeled. And I noticed that A and B do not overlap. There's no common area between A and B, which means that the intersection of A and B is 0. Okay? And also, I see that the region shared between A and C is 2. So the probability of, I don't know why I put P. It's supposed to be N. P of A over C has to be 2 divided by 29 because that's the total number of things, okay? So 2 over 29 is the answer for that. And then the probability of A prime intersection C is the probability of, let's see, so A prime intersection C means I'm not in A, I'm outside of A. Okay, I'm outside of A, and I'm also inside of C. Okay, so what does that mean? I am in I'm outside of A and I'm in C, which is basically this area here. Okay. And that should be 14. I think the working out here has a bit of a weird thing. That area is 14. Okay, so this should be 14 over 29. I forgot to convert these back into probabilities. 14 over 29. Let me check the Q&A. Can you give an example of mutually exclusive events? Yes. You either get a 7 or you get a 6 on your test. You can't get both. It's a bit of a dumb example, but yeah. Conditional probability is the probability of an event A happening, given that we already know that event B has occurred, all right? And it's calculated by taking the probability that both events occur, divided by the probability of knowing both events. And let me kind of put this in perspective. Let's say that at your school, you need to score 90% on a test to get a 7. Okay? Um, and it is, let's say it's given that you scored more than 85%. Okay? You don't know exactly what you scored yet, but you know it's greater than 85%. Once I tell you this, your chance of scoring a 7 has, it theoretically has now increased because uh, you're at least greater than 85. All of the chances that you had scored below 85 are now excluded. And so essentially you're only left with the possibilities that you scored above 85. And many of those probabilities are going to lead you to a 7. And maybe I can show you on a, well, I'm not going to show that because I'll do a different Venn diagram. So the conditional probability is basically like, let's say that this is A and this is B. Okay. Now, the probability of A in general is the number of things that are in here divided by the number of things that are in the overall universe. Okay. Now, oops, let me just plug in my iPad. The probability of A given B, well, A given B means both that A and B happened. So it means that I'm dealing with this area here in the middle. But I also know that B has happened. So the number of total possible cases that I'm dividing by is not the total number of things in the universe anymore because I know that B happened. So now you're kind of inside of a smaller universe, if you will, where B has happened. And therefore, I'm only going to do this area divided by this area. Okay? And that is the formula that I have. Okay, so the formula tells me that the probability of A given B is the probability of the intersection divided by the probability of the one that is given. Okay, so let's do an example. It is given that P of A given B is equal to 0.7 and P of B is equal to 0.5. And also that P of A union B is 0.6, and we want to find P of A. So what do I know? I know that P of the A and of the union is the sum minus the sum of the probabilities minus the intersection, and that's supposed to be equal to 0.6. Okay, and also I know that P of B is 0.5, and because I have P of A given B is equal to P of A intersection B over P of B, I can write the intersection A intersection B as P of A given B times P of B. Okay. And I'm doing that because those are the things that I know, and I don't know what the value of P of the intersection is. Okay. So I write the intersection as P of B times the probability of getting A given that I have B. And that gets me to this equation here. And I know now that P of A given B is 0.7 and that P of B is 0.5. So multiplying them together gives me 0.35. And if I simplify everything, find that the probability of A is 0.45. All right. So a lot of the kind of questions in IB I guess tricky with probability are about working with these weird, I wouldn't say weird, working with these formulas and doing a bit of rearranging and making some substitutions. It's kind of like basic algebra, but with these probabilities thrown in, and that does make it a little harder. But I don't think it's honestly the trickiest of topics. Okay, we're gonna do sort of IB style problem here. Um, I want you, I'm gonna give you probably 5 minutes to get started on this, and then we'll sort of continue from there. I have this Venn diagram with students who ate, what is it, sushi, risotto, and quiche. It's quite a fancy combination. And there are 150 students recorded. They're shown in the following Venn diagram. And first, we want to find the probability that a randomly selected student ate only quiche. So we're looking for students in there. So quiche is 45, only quiche, and we're dividing that by 150 to be that's the total number of students. I'll divide both those by 5. I'll get 9 over 30. And divide that by 3. That's 3 over 10. Okay, so 3 over 10 is my answer to AII. To AI, I mean. A point I, and then AII. The probability that a student, randomly selected student, ate only one of the dishes. Okay, so one of the dishes would mean either only risotto, or only sushi, or only quiche. So I can do 51 plus 24 plus 45 divide by 150. And 51 plus 24, it's going to be 55, 75, plus 45 is going to be 120 over 150, which is 12 over 15. Divide both of those by 3, it's 4 over 5. Okay, so 4 over 5, not 4 over 4. Okay, let's check these off. We found, I want to say 3 over 10 and 4 over 5. Now, it is given that 25 students ate 2 or more dishes, okay? So we need to find the value of C from that. So 2 or more dishes corresponds to this entire region here, okay? So that means that A plus B plus 9 is equal to 25. Now, how does that help me find C? Well, now I know everything that's in the intersection of S and R or S and Q or all three. Which means that if I add that to the number of to n of S plus n of R plus n of Q, which is the number that we found in the previous, it was this 24 plus 51 plus 45. That gave me 120. So that's equal to 120, which means that C, the number of students who didn't eat, is just the number of students who ate. So number, let's say, 1 dish plus n 2 plus dishes, I guess. That's 120. Sorry, and it's supposed to be let's say all of that, C plus all of that is 150, the total, okay? So 150 is equal to 120 plus 25 plus C. That means that C is equal to 5. Okay, let's check that off. I have a question here. Do we have to simplify the probability? I mean, no, strictly speaking, you don't. I generally do it because first of all, you just never know. It takes me 5 seconds, and I prefer to do it than have the uncertainty of, oh, am I going to lose a point? The mark scheme says you shouldn't lose a point for an unsimplified fraction. That being said, sometimes if the number that you found is going to be useful in the next parts, if you don't simplify it, then the work you're going to have to do in later parts is going to be a lot harder. So I always think as a matter of just sort of like good habit, it's nice to clean up your fractions. But strictly speaking, according to the mark scheme, it's not required. Now, find the value. We just did that. Find the value of C. I was checking that off. C was equal to 5. Okay. But the conditional probability formula tells me the probability of A given B is equal to the probability of both of A intersection B divided by the probability of B. Okay. So we're looking for the probability that a randomly chosen student ate all 3 dishes given that they ate sushi and risotto is 0.25. So I'll write 0.25. And then what's the probability that they ate all 3 dishes? So if they ate sushi and risotto and they ate all 3 dishes, they'd still just ate all 3 dishes. So all 3 dishes is B. And the probability that they ate sushi sushi and risotto is this interval here. It's A plus B, right? Okay, so that's A plus B. And let's remember what I knew from part C, which was that A plus B plus 2 plus 7 was 25 students in this intersection, right? And that means that A plus B is equal to 11. All right, that is, no, I made that up. Shouldn't be 11, it should be 16. A plus B is equal to 16, okay? Now, that gives me in this formula, B over 16 is equal to 0.25. 0.25 is 1 over 4, so I can tell that B is equal to 4. And that tells me that A is equal to 12. Okay, let's check that off. A is equal to 12, B is equal to 4. And I have a question. The question says, can you do it without the formula? Let me see. Given that, I mean, you can not write the formula. You can think about it. You can reason it out. But under the hood, of whether you know it or not, you're going to be using the formula. Because the formula, it's not some special fancy formula. It's just kind of like this logical formula, and I may go over the logic in a second, that explains why the given probability relates to the probability of the intersection divided by the probability of the given. Okay, so You could kind of try and use your brain and intuit it, but you're going to actually be doing the same math under the hood. You just won't be necessarily as aware of it. Okay, next part. Now, independent events. So we say that two events A and B are independent if knowing that one event occurred doesn't change the probability or expectation that the other will occur. Mathematically, that means that the probability of both happening is just the product of the probabilities. So one of them does not affect the other. And in other words, it means that the intersection divided by P of B is, which is the same thing as P of A given B, is just P of A. So basically, the probability of A given B is just the probability of A. That means that the probability of B does not change the probability of A happening. Okay? So let's look at an example. Let's consider two independent events A and B, where A intersection B is 0.2 and the probability of B is 0.8. All right. So because they're independent, I can say that the probability of both is just the product of the probabilities. And that means I take what I have 0.2 is equal to P of A times P of B, which is 0.8. I solve for P of A and I get 0.25. So I'm given the events A and B, and I know that the probability of A is 0.4 and the probability of A and B is 0.8. So first we want to find P of B in the case where A and B are mutually exclusive. So if they're mutually exclusive, it means that the probability of both of them happening is 0. So let me write out what that means. Hello, can you hear me? Was my audio working a second ago? It looked like it wasn't. It was working. Okay, I'll continue. All right. So let me write out what I know. If they're mutually exclusive, it means that the intersection is equal to 0. And therefore, that P of A union B is P of A plus P of B. And normally I would do minus the intersection, but that's just minus 0. So 0.8 is equal to 0.4 plus P of B. And so P of B is equal to 0.4. Okay? That is my answer for part A, 0.4. Now, in the case where A and B are independent means that the conditional probability of P of A given B is the same as P of A. Or in other words, that the probability of A intersection B over P of B is equal to P of A. And the intersection is, well, I can say that P of A union B is equal to P of A plus P of B minus P of the intersection, which means that the intersection on its own, I can say the P of the intersection is equal to, well, P of A is 0.4 plus P of B, and P of the union is 0.8, so minus 0.8. Okay, and therefore I can plug that into the formula I have above and say that P of, so that whole thing, so P of B basically minus 0.4 divided by P of B is equal to P of A, and P of A is 0.4. All right, now let me just make a bit of room and we'll continue. That means that P of B minus 0.4 is equal to 0.4 P of B. Or if I subtract 0.4 P of B from both sides, it's 0.6 P of B is equal to 0.4. So P of B is equal to 0.4 over 0.6, which is equal to 4 over 6, which is equal to 2 over 3. And that should be my answer for part B. Okay? Let's check that off. 2 over 3. 2 over 3. All right, checking for questions. No, it seems like we're good. All right, then part C. We're actually given the conditional probability P of A given B is equal to 0.2. And let's remember that that's equal to P of A intersection B over P of B. And we found that the intersection was equal to P of B minus 0.4, right? And then this is divided by, remove that so it doesn't look like a minus, divided by P of B. All right, so that means that 0.2 P of B is equal to 1 P of B minus 0.4. In other words, I have 0.8 P of B is equal to 0.4, so P of B is 1 over 2. That is my answer. P of B is 1 over 2. So here I have a harder problem. This is a really hard problem. Honestly, probability on the exams has not really shown up as a very difficult question. But my goal is to make sure you're ready for hard questions in every topic. So I'm going to give you 5 minutes to at least get started on this, get a head start on me, and then maybe I'll actually give you like 8 minutes because this is a long question. I'd like you to really try, even if it's hard and you don't get it. I'd like for you guys to struggle with this. It'll help you get better. All right, let's go over this. So we're going to start from what we know to be the definition of P of A union B, which is P of A plus P of B minus the intersection. Okay, so that means for x prime and y prime, that's P of x prime plus P of y prime minus P of x prime and y prime. Okay, so what next? I can say, therefore, that that's equal to 1 minus P of x, because the probability of x not happening is the opposite of the probability of it happening. Same thing for P of y prime. And then, because x and y are independent, x does not affect y, and that same is going to be true for the complements. So that means I can write this as P of x prime, P of y prime. They are independent. Okay? Now, I can write this as 2 minus P of x plus P of y for now, P of y, then minus, and then I'm going to do the same thing for Px prime here, 1 minus P of x times, and that's supposed to be capital X, and this one too, x, 1 minus P of y. Now I expand as much as I can. That's 2 minus P of x minus P of y, and then I'm going to have minus 1 minus P of x minus P of y plus P of x, P of y. Okay, and I think they're about to lose sight of me, so I'm just going to fix the position quickly. We'll do this. That's better. Okay, now I can continue. I'm just going to come up here and say that that's equal to, so I have 2 minus P of x minus P of y, 2 minus P x minus P y. Then I have minus 1. I have plus P of x plus P of y. And then I have minus P of x, P of y. What does this all become? I'm going to get 1 minus the px and is going to cancel with the px, and py is going to cancel with py. And I get 1 minus P of x, P of y. And px, py, because the events are independent, is the same as the probability of x intersection y. I have a question, so let me check what it says. Is px prime intercept y prime equal to p? I mean, that's essentially what this is saying. That's what this question is saying. It's saying that I can apply the complement to the whole thing. It's saying it in a way that like I think the statement that you're saying would be a bit confusing to write on an exam. But yes, it's exactly equivalent to what I just said, or to what we just proved. Okay. Now, clear my screen. And we did that because that was a necessary thing to solve so that we could have that result for part B, and I think also for part C. So what are we trying to do? We know that P of A prime union B prime is equal to 0.9. And I can say that that's equal to P of A prime plus P of B prime minus P of A prime intersection B prime. And so far, that's just me using the definition of the union. And I know that this thing here is 0.4. So that means that 0.5 is equal to P of A prime plus P of B prime. All right, the sum of those add up um, to 0.5, okay? And then what can I do? Well, I'm trying to find the product of A and B, which is basically the product P of A, P of B. And how do I relate that to what I have? Well, I know now that I can write, and I should probably write also just over here. Let's remind ourselves that P of A intersection B is equal to P of A, P of B, because the events are independent, so that's equal to AB. Now, I can use the result from part A to say that that is the same thing as 1 minus the intersection, 1 minus the intersection of the opposite. So 1 minus P of A union, A prime union B prime. That's what we found. This is the part that I'm interested in, the AB. So I do 1 minus the other side, okay? So I'm looking for 1 minus P of A prime, B prime, which is 1 minus 0.9, and this is just equal to 0.1. So actually, the work I was doing here is for part C. We don't need to do that yet. So AB is equal to 0.1. All right, now AB is equal to 0.1. We'll move on to part C. Let's erase this. Dun, 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 dun. Now, looking at part C, and I want to use the result from part A, but I need to do something actually extra tricky. What I'm going to say is I'm going to say let x equals to A prime and y is equal to B prime, so that x prime is equal to A prime prime, which is just A, sorry, which is equal to A, and y prime is equal to B prime prime, which is equal to B. Okay? That means I can say that the probability of A union B can be written as 1 minus the probability of A prime intersection B prime. So that would mean that 0.9, sorry, that, what am I saying? That's not the correct thing to say. That P of A intersection B, A intersection B, of A union B, sorry, A union B is equal to 1 minus 0.4, which is 0.6. Okay? And I also know that the union of A union B is P of A plus P of B minus the intersection. And these are independent events, so so that's just going to be the product. So I'm going to have P of A 0.6 is equal to P of A plus P of B minus AB, and we found that AB was equal to 0.1. Okay, and now let me erase this and set up my equation. That means that A plus B is equal to 0.7. And if I know that AB is equal to 0.1, then I can say B is equal to 0.1 over A. So A plus 0.1 over A is equal to 0.7. And now what I'm going to have to do is multiply both sides by A, and that's going to lead me to a quadratic. So let me make a bit of space here, because we need more space. And what do I find? I find that A squared plus 0.1 is equal to 0.7A. Now I can solve that. I can bring a squared minus 0.7a plus 0.1 is equal to 0. So a is equal to 0.7 plus or minus the square root of 0.49 when I square 0.7, minus 4 times a times c, so that's minus 0.4 all over 2, and that's equal to 0.7 plus or minus the square root of 0.09 over 2. And I know what that is. That is, I need to make more room again now. Let me go over here, actually, there's a bit of space here. That's 0.7 plus or minus 0.3 over 2, which gives me either 1 over 2, so 0.5, or 0.4 over 2, which is 0.2. Now, because a is less than b, I know that a has to be less than half, because if a was half and b is bigger than a half, then they would add up to something bigger than 1. Okay, so I must have a is equal to 0.2. Okay, because it's the bigger one. If a was let's say 0.5, then b would be bigger. Okay, so that one cannot work. Okay, so we're going to talk about selection with and without replacement. And this kind of links a little bit with counting, but in a very basic way. But in probability of selection is the action of choosing one or more items from a set or group, which is why I say this is a little bit like counting. And you can perform these selections either with replacement or without replacement. So when I replace, it means that every item is returned to the original group before the next choice. So the probabilities don't change across selections. And if I don't have replacement, then when I remove an item, it changes the group and therefore changes the probability of each subsequent pick. So let's see an example of both. So let's say Julia selects 3 marbles from a bag containing 3 blue marbles and 6 yellow marbles. We want to find the probability that Julia selects 3 blue marbles if A, the marbles are replaced after each selection, and B, the marbles are not replaced. So if the marbles are replaced, the probability doesn't change. It's always going to be the number of blue marbles, so 3, divided by the total number of marbles, which is 9. So that's 1 over 3. And if I do that 3 times, the probability is going to be that to the power of 3 is 1 over 27. Okay, so that's pretty straightforward. Now, if the marbles are not replaced, the number of blue marbles in the bag is going to change every time. At first, I have 3 blue marbles out of 9 total marbles. That's 1 over 3. Then I have 2 blue marbles out of 8 total marbles. That's 1 over 4. Then I have 1 blue marble out of 7 total marbles left. That's 1 over 7. And I multiply each of those together. 1 over 7 times 1 over 4. Sorry, 1 over 3 times 1 over 4 times 1 over 7. It gives me 1 over 84. Okay? Now, it's often very, very helpful to represent these with what we call a tree diagram. And it's a very powerful visual representation for multi-step probabilistic events. And it's not just a tool you can use, it's a visual that the IB is going to expect you to be familiar with. You might have a question that shows a tree diagram for you to fill in. On a tree diagram, each branch is going to split to represent a different outcome at each stage. And the probabilities are written along the side of the branch. And then to find the probability of a particular combination, we multiply the probability of getting to that outcome along the branches. All right. So if I wanted a green marble and then a red marble, it means I'm doing this branch here. I'm going green and then red. So I would do 5 over 12 times 7 over 11. Now, here's an example. I'm drawing marbles from a bag containing 7 red marbles and 5 green marbles. Jack draws 2 marbles from the bag, and we want to find the probability that he selects 2 red marbles, and then in a separate case, 2 marbles of different colors. So we fill in the probabilities on the different branches of the tree. So the probability that the first marble is green is 5 out of 12, and for red, it's 7 out of 12. After drawing the first marble, there are 11 left. There's also 1 fewer red/green marbles. So I can then fill in 7 over 11, 5 over 11, and 6 over 11. And I think this should also be, that is supposed to be, I want to say 4 over 11. I can't remember. Yeah, 4 over 11. 4 over 11 for a second green. I just forgot to fill that in. Let me put it in. I don't think it's actually relevant in this case, but 4 over 11. And yeah, so now that I have all those branches filled in, the probability of drawing 2 red marbles means I did this. So I just multiply 7 over 12 by 6 over 11, and I get 7 over 22. Now, the probability of drawing 2 marbles of different colors is either I draw a red and then a green, or then a green and then a red. So what I do is I first consider this probability here, 5 over 12 times 7 over 11, green then red, um, and then I add 7 over 12 times 5 over 11. And if I add both of those together, I'm going to get 70 over 132, which is the same as 35 over 66. All right, here is a IB style question about tree diagrams. So I'm going to give you 5 minutes to try this on your own, and then we're going to go over the solution. Okay, let's go over the solution to this. So I have this tree diagram representing the outcomes from selecting marbles from a bag that has B blue marbles and R red marbles. And 3 marbles are selected at random, and therefore I have a depth 3 of branches here. I'm also told that the ratio of blue marbles to red marbles is 5 to 3. What does ratio mean? Well, ratio means that if I have something like 5K blue marbles and 3K red marbles. And in total, that means I have 8K marbles, some multiple of 8. Now, what I can see is that the probability of selecting a blue marble, having already selected one red and then blue, so I can write that as probability of blue, or actually of, you have to write this in full sequence of R, B, B, given that I already selected RB, is equal to 22 over 35. Now, what is the probability of selecting a blue marble given that I've already selected one red marble and a blue marble? Well, if I have 5K blue marbles, that means I selected one of them. I have 5K minus one of them left. And how many marbles do I have total? I started with 8K and I've selected 2 marbles, so I have 8K minus 2 left. And that should be equal to 22 over 35, whether simplified or not. All right. Now this looks like it's going to be a bit of a mess to expand, and it is slightly messy, but it's not actually terrible. What I can do is I can say 35 times 5K minus 1 is equal to 22 times 8K minus 2. Okay, like that. And if I expand both of those, 5 times 35 is 175K minus 35, and 22 times 8, this is also a calculator question, so you can use that. 22 times 8 is 176K, then minus 44. All right, and that's great because I have 1K more on the other side than the other, so if I cancel it out, I'm going to have 44 minus 35 is equal to K, and that tells me that K is equal to, this is just 9. Okay, so K is equal to 9. And I know that I have 8K total marbles, so I have 72 total marbles. That's N. That's the answer for part A. Now, part B, we're trying to find the probability P. And the probability P is on the diagram here. The probability of selecting a red marble, given that I selected already 2 blue marbles. So let me erase and remember what I know. I have 5K, which is 45 blue, and 3K, which is 27 red to start with. And then after selecting 2 blue marbles, I have 43 blue left, 27 red left, for a total of 70. Okay? So that means that P is equal to, probably getting red is 27 over 70. And I don't think I can simplify that any further because it's only a factor of 3. So yeah, 27 over 70 is the answer for B. Okay? Let me check both of these off quickly. So we found 72. And then we now find P was 27 over 70. All right. Now we want to find the probability that at least one red marble and at least, and blue marble are selected. So out of 3, I selected at least one of each. And the way I'm going to do this is to do 1 minus the probability of of 3 red marbles, of R, 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 or B, B, B. So the ways I can select one of each marble is the ways that I don't select only one marble. So again, some sort of mirrors here to the counting unit. But if I write this out, I can do 1 minus, and the probability of selecting 3 red marbles, well, I start with 27, then I would have 26, and then I would have 25. out of a total of 72 times 71 times 70. And something similar for the probability of 3 blue marbles. So let me just make some room here, and we'll do that. 3 blue marbles is I started with 45, then times 44, then times 43, over 72 times 71 times 70. Okay? Now, for this, I'm going to need to use my calculator. So out comes the TI-84. It's a bit too messy. And I'm going to have, I can simplify one step further and say 1 minus, put them over a common fraction at least, 72 times 71 times 70. And then 27 times 26 times 25 plus 45 times 44 times 43. All right, that's the best I can do. Now I'm going to actually perform that fraction. So I'm going to do 27 times 26 times 25 plus 45 times 44 times 43. Divide that by 72. Make sure I put brackets. 72 times 71 times 70. And if I write that as a fraction, I find that is 1 minus 163 over 568. Okay, so now I do 1 minus that, and I get 405 over 568. Now, you don't have to write this as a fraction necessarily. You can write it as a decimal, that's fine. If your calculator spat out a decimal, you don't have to convert it, but I get 0.713. Okay, checking for questions. I don't think. Nope, seems like we're good. I'm gonna check it off and we'll continue. 0. Which one was it? It was 405 over 568. Okay. Now, we're almost at the end, and we have to talk about Bayes' theorem. And this is a little bit annoying because Bayes' theorem has not showed up on the exams, and yet the IB says that you have to know it, and they're quite insistent. It's not just kind of like one of the side things. They fully made like a separate course code for Bayes' theorem, and there's nothing else but Bayes' theorem in it, and then they never do it. So look, we're gonna learn it. It's not that difficult to understand, and just in case it shows up, then you will be ready. So Bayes' theorem allows us to reverse conditional probabilities. And it basically uses a way of finding P of B given A, knowing P of A given B and other information. So we have a bit of a messy formula, and it's in your booklet, so you don't need to memorize this at all. And I'm not even going to bother kind of like showing you where this came from or going through it because it's honestly it's a bit tedious. But basically, what Bayes' theorem allows us to do is update our beliefs or predictions or alter this probability given certain evidence, okay? And it's particularly useful when dealing with sequential information and when I'm getting like new data continuously. And the classic example of Bayes' theorem is imagine that you have a medical test for a rare disease, okay? And 1 in 1,000 people have this disease. And let's say that the test for this disease correctly identifies the disease in 99% of patients who have it, and it has a false positivity rate of 1%. All right? Now, let's imagine that you test positive for this rare disease. What's the probability that you actually have this disease? Well, let's let B be the event. Person has the disease, okay? And we know that's 0.001 because it's 1 in 1,000. And A be the event, a person tests positive. And we know that the probability of testing positive if you have the disease is 0.99, and the probability of testing positive if you don't have the disease is 1% or 0.01. Then I can say that the probability of having the disease, given that you tested positive, is, using my formula, I do the probability of A given B times the probability of B, 0.99 times 0.001, divided by the probability of B times probability of A given B, plus the probability of not of B prime times probability of A given B prime. And if you actually calculate it out, you'll find that you have a slightly over 9% chance of having the disease, even if you test positive, which is strange. You have this 99% accurate test, and you just tested positive, and yet your chance of getting the disease is only 9%. And this should illustrate a pretty useful or at least like interesting fact that when you have an event that is much more rare then the tool that you use, then the accuracy of the tool that you're using to diagnose that, the probability is going to be much lower than the accuracy of the test. It's going to be somewhere between the probability of the event in general and the probability of testing positive, right? So, and between the accuracy of the test. So it's a pretty interesting fact, and it shows up oftentimes. Oh, can you explain the denominator using the words of the question itself, not A and B? Oh, yeah, so the denominator here would be, so I take, so in the numerator, I have P of A given B. So it's the probability that you tested positive, given that you have the disease, times the probability that you have the disease. And if you think about it, I know that P of A given, sorry, I should write that better. P of A given B is P of A intersection B over P of B. And so actually this numerator is just P of A intersection B. It's just P of A intersection B. So basically the numerator says the probability of having the disease and testing positive. And in the denominator, I have the probability of B times P of A given B. So that's actually the same thing. That's the probability of both of those things plus the probability of not testing positive. So this is the probability of having the disease or testing positive and not having the disease. So that's what this formula actually says. So what it means is I'm dividing the probability of having the disease and testing positive divided by the total excuse me, the total probability um uh of testing positive, which is the probability of testing positive and having it, and the probability of testing positive and not having the disease, which is why I have this sum down here. Okay, maybe I think that probably helps explain it. And just in general, I think that helps illustrate this formula. This formula looks very complicated. It's actually the same as this. It's just that we write it in the more complicated form because we use this formula when we have conditional probabilities that we're trying to invert, right? So when I know the probability of testing positive given the disease and vice versa, it's not when I know these probabilities. That would be almost less easy. But the way this theorem is proved is by kind of starting with this and working backwards to that. Okay, let me clear my screen. So the reason that Bayes' theorem is often not really covered in the syllabus is because you don't actually need the formulas from Bayes' theorem to solve problems that are related to Bayes' theorem. And I'm going to show you that in this example. This is a hard IB style question. Again, it's nothing very similar to Bayes' theorem has showed up, but it could show up. And this is one of the ways it might. And we are told that in Anchor Lake, exactly 1/3 of fish are infected with a parasite. And we have a diagnostic test that successfully identifies the infection in 9 out of 10 positive cases and has a false positive rate of 3 out of 10. Let's start by writing down what that means in terms of probabilities. It means that the probability of testing positive if a fish is infected is 0.9. And the probability of testing positive if a fish is not infected is 0.3. All right, and we're trying to, in part A, show that the probability that a single test comes back positive is 1 out of 2. Okay, so what is the probability of a positive test? Well, it's going to be the probability of a positive test given the fish is infected times the probability of an infection. So the fish is infected and it tested positive, plus the other case, which is a positive test in a healthy fish. So this is a false positive and again, times the probability of the fish being healthy. So times pi prime, like that. Okay, so let's calculate each of those. I know the first one is 0.9 times, and the probability the fish is infected is 1 in 3. And then the probability of a false positive is 0.3, and the probability of a fish being healthy, not infected, is 2 out of 3. So this is times 2 out of 3. Okay, this comes out to 0.9 times 1 over 3 is 0.3. And then 0.3 times 2 over 3 is going to be 0.2. And that comes out to 0.5 or 1 over 2. Okay, so that's part A. And now in part B, we're trying to find the probability that the fish is infected. So we're trying to find, the probability that the fish is infected given that its test result came back positive. So what is the probability of infection given T plus, okay? And that's the opposite, by the way, of the probability of a positive test given I. So this is, how we know or even start to think about Bayes' theorem is that we're looking for a conditional probability opposite to one that we know. And let's remember what we know otherwise, which is the probability of a positive test in a non-infected fish is 0.3. Okay? So I'm going to write this formula out without Bayes' theorem, just to show you that Bayes' theorem is kind of a slightly useless equation. And simply say, well, I have a conditional probability, and I can apply my regular conditional probability formula. This is going to be the probability of infection and a positive test divided by the probability of a positive test. Okay? Now, what is the probability that a fish is infected and tests positive? So there's a 1 in 3 chance of being infected. So there's a 1 in 3 chance of being infected. And if the fish is infected, then there is a 9 in 10 chance of testing positive. So 9 out of 10. Okay? And the total probability of testing positive, that's what we found in part A. That's 1 over 2. And so this is going to come out to 1 over 3 times 9 over 10 is going to be 3 over 10. 3 over 10 divided by 1 over 2 is going to be equal to 3 over 5. Okay? Let's check that answer off. 3 over 5. Now, in part C, we're told that a second test on the same fish comes back positive, and we want to find the probability that the fish is healthy. That probability is P not infected given, let's say, T1 plus and T2 plus, so 2 positive test results. Now, again, I don't need to use Bayes' theorem. I can use regular conditional probability formulas and say that this is going to be equal to the probability of all 3 of those things happening. So, the fish is healthy and tests positive a first time and tests positive a second time, divided by the probability of 2 positive tests. Okay? So that numerator, the probability of not being infected but testing positive. So if the fish is not infected, there is a remember P of not being infected is 2 out of 3. Okay, so it's going to be 2 out of 3 probability of not being infected, then times the probability of testing positive given the fish is not infected, which is 3 out of 10, and times that again because there's a second positive test result. We're assuming in this case that the test results are independent, which is to say that there was no error in the test that was due to anything special about the fish. It was just random error, which is something you should do in the IB unless you're told otherwise. Okay? And now what is the probability of testing positive twice in general? Well, it's going to be this probability that we found, which is 2 over 3 times 3 over 10 times 3 over 10. That's the probability of 2 positive tests if a fish is not infected. And if a fish is infected, then that probability of being infected is 1 over 3. And then the probability of testing positive is 9 over 10. And again, second time, 9 over 10. All right, now this is a bit of a mess, but let's simplify as much as we can. I have 2 over 3 times 3 over 10 is going to become 2 over 10, or 1 over 5. So 1 over 5 times 3 out of 10. And that is going to be divided by, let's simplify as much out as I can. I have that same probability, and remember the first part in the sum is the same thing, so it's 1 out of 5 times 3 out of 10. And then I'm adding, well, I have 1 out of 3 times 9 out of 10 is 3 out of 10, then times 9 out of 10 again, so that's going to be 27 out of 100. All right, and now in the numerator, I'm going to make this 3 out of 50. That's the first step. And then in the denominator, I'm going to have 1 out of 5 times 3 out of 10. That is going to be 3 out of 50. But I'm going to make it out of 100 so it has the same denominator as the other fraction. So 3 out of 50 is 6 out of 100. 6 out of 100 plus 27 out of 100. And then I'm going to make the numerator also out of 100. It'll make things easier. So I'm going to have 6 over 100 divided by 33 over 100. And now it's just going to simplify to 6 over 33. And 6 over 33, there's a common factor of 3, so I can say it's 2 out of 11. Okay, that is my final answer. And I'm going to check that against the solution. 2 out of 11 is indeed correct. Nice. Now, the last thing that we need to talk about, because it's on the syllabus and I don't really know why, is Bayes' theorem for 3 events. Okay, when I have complementary events B and B prime. Okay, so we used Bayes' theorem before when I either had the fish was positive or the fish was negative, right? I either had an infection or I didn't. Now, it's worth considering with Bayes' theorem the events of the type where I have B1, B2, or B3, and one of those has to be true. Okay, so for example, I could have the event B is someone has COVID, and B prime is someone does not have COVID. But we might also have B1, someone has COVID, B2, someone has the flu, and B3, someone has neither. And obviously, someone could have both, but for the sake of imagination, let's imagine that's not the case. So in this case, I can generalize Bayes' theorem, and it just gets even messier. It's still in your formula booklet. And this, I think, is very, very unlikely to show up on the IB, given they've never even done, this case. But it basically is the same formula and the same logic and the same procedure. You just have one extra thing in the denominator. You now have this P, this third one, P of B3 times P of A given B3. And I'm going to show you an example of it just for the sake of your understanding, but we're not going to do a problem on it. So a patient is presenting with a fever, and it's believed that they either have COVID or the flu. And it's given that at the moment, 80% of COVID patients and 95% of flu patients have fevers. And 10% of patients who don't have COVID or the flu have a fever. And we also know that at this moment, 2% of people have COVID and 3% have the flu. And we want to find the probability that the patient has COVID. So we let A be the event that the patient has a fever, B1 be COVID, B2 be the flu, and B3 be neither. And we know that the probability of having COVID is 0.02, probability of having the flu is 0.03, and therefore the probability of having neither is 0.95, okay? Now, we also know that the probability of having a fever if you have COVID is 0.8, and the probability of having a fever if you have the flu is 0.95. And the probability of having a fever if you have nothing is just 0.1. You just have a random fever. And therefore, I can say that the probability of having COVID, given that you have a fever, is, I use my formula, the probability that you have COVID, 0.02, times the probability of having a fever if you had COVID, so 0.8, and I divide by that same thing, but then I also add the case of the probability of you having a fever if you have the flu, times the probability of having the flu, the probability of having a fever if you have nothing, and times the probability that you have nothing, and I add all those up in the denominator, and I end up with a result of 0.015. So it looks like a mess. Conceptually, this formula is basically just saying it's the same as P of A intersection B1. So you have divided by P of A intersection B1 plus P of A intersection B2 plus P of A intersection B3. And I'm a little bit out of space there. But what this is saying is that I just take, in the numerator, the combination, the intersection of both things that I'm interested about, divided by all the different ways I could have had a fever. So I could have a fever with COVID, with the flu, or with nothing, and I add all those cases up, and that is my denominator. All right. So I'm going to stop the screen share there. That's everything we were going to talk about today. I'm going to get the recording posted soon and sort of fix it because I didn't do super job at 2 different pieces. I'm going to post exercises also if you guys want to try those. And I'm also going to just send out my little poll before you guys head out. My favorite part of the day. Launch that. And yeah, so if there are any questions, you can stick around or ask a question. I'm stopping the recording now. So everyone who's watching recorded, thank you for watching.